Okay, so today we're talking about the zeros of the polynomial. And remember, you have to know how to do synthetic division to really go forward into this section. And the first thing they talk about in here is the rational zeros theorem. And this can look intimidating, but it's not. So don't panic or don't think this is overwhelming. It is not overwhelming in any form or fashion. But what the rational zero theorem does for us is it helps us to find a number we can put into synthetic division and get a remainder of 0. Okay, so its goal is to help us find a number to start with to put into synthetic division and get a remainder of 0. And that's what this says, how to find the first 0 to put through synthetic division to get the remainder of 0. So the rational zero theorem gives me this thing with this P over Q, which is very hard to understand from the theorem, but if I go straight to an example, you'll see that it's really not difficult. So what we do is they give us a polynomial, and the number on the end, or the constant on the end, will be your p value. The leading coefficient of the polynomial, the number in the front, is considered your q value. So we come over here and we say, all right, p is negative 15, and q is a positive 4. And we list the factors of each of these numbers. And we list the positive and the negative factors, not just the positive, but both the positive and negative, so we put plus minus in front of them. So all of the factors of 15, 1 will go into 15, and we put the plus minus. 2 does not. 3 goes into 15. 4 does not. Of course, the 3 times the 5 is the 15, and the next factor you would have would be 15 itself. So those are the factors of negative 15. The factors of 4, there's not too many of these, would be 1 and 4, and then 2 and 2. So it only has 3 factors. So the question says, list all possible rational zeros, which means here comes a bunch of numbers that we can pick from to try to put through synthetic division until we locate one that will give me a remainder of 0. So I'm supposed to come up with the p's over the q's, which are my possible rational zeros. In other words, in this list, there's bound to be a number that would work in through synthetic division with a remainder of 0. So I take the p's over the q's. So if I start with 1, I take 1 over 1, 1 over 2, and then 1 over 4. So this becomes plus minus 1 over 1, plus minus 1 over 2, and plus minus 1 over 4. So that's my p value of 1 over each of my q values. Then I come in here and I take my p value of 3 over each of the q values. So that becomes plus minus 3 over 1, then the plus minus 3 over the q value of 2, then the plus minus 3 over the q value of 4. Then I take the p-value of 5 over each of the q values. So a p-value of 5, I take the 5 over the q-value of 1, the 5 over the q-value of 2, and the 5 over the q-value of 4. Then I take the p-value of 15 over each of the q values also. So the 15 over the 1, the 15 over the 2, and the 15 over the 4. Now once you get all of these listed out here, and these are plus minuses, and on this tablet sometimes they don't look so great, but those are all plus minuses, which is 2 values each. All of those numbers in a list are my, quote, possible rational zeros, which means one of those numbers or more would work through synthetic division, giving a remainder of 0. Now, often you'll have a repeat, but I think that they've selected this question purposely that there are no repeats. So these are your possible, and sometimes they call them potential rational zeros. Okay, so you take the p's over the q's, and they're always the plus minus. Okay, so now let's go more into a real example in which you could apply these rational zeros. So it says factor the following polynomial, but begin by listing all of your possible rational zeros and then factor it. Okay, so the number on the end is your p value and the leading coefficient is your q value. So your P is -6 and your Q is 2. So you come in here and you list all factors of the P and the Q, and don't forget you use the plus minus, okay, positive and negative. So of 6, you'd have plus minus 1 times 6, then you'd have plus minus 2 times 3, and that would be the list of all the factors of the p-value of 6. If you want to list the factors of your q value of 2, now that's going to be pretty easy. Plus minus 1 and plus minus 2. And really, officially, I should put a comma between those, but it looks kind of messy on my tablet when I do. But if you were listing these in your homework, you really should put commas between them. So now if I need to list my p's over my q's, my true possible rational zeros, the possible ones, not the actual ones, but the possible ones. I think I'm out. Were there any more handouts, guys? Anybody have an extra one? Yeah, I'm sorry. I don't think I'm out. Okay, so this would be, start with the p-value of 1 and take it over the q values of 1 and 2. So plus minus 1 over 1 and plus minus 1 over 2. Then take the next p-value over the q's, which is plus minus 2 over 1 and plus minus 2 over 2. Then take the 3 over the q values, plus minus 3 over 1 and plus minus 3 over 2. I really should have commas between these, but again, it's kind of hard for me to fit them in here. Then take the 6 through, plus minus 6 over 1 and plus minus 6 over 2. Okay, so if I can slip little commas in here or something like this. These are your possible rational zeros, but this list does have a repeat. For instance, 2 over 2 is just 1, and you have 1 in the list also, so you can eliminate that one from the list. There is another one in this list you could eliminate. What would that be? The 6 halves, because that's just 3. So that kind of limits it a little bit. So really I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible rational zeros. Now I have to go to this list now and take a guess, a random guess at wondering which one of these will work through synthetic division and give me a remainder of 0. So what I want to do is I want row 1 of you in this classroom, all you on the first row, I want you to take a positive 1 through synthetic division and see if you get a remainder of 0. Okay. Row 2, I want you to take the value of 2 and put it through synthetic division and see if you get the remainder of 0. Row 3 of this classroom, I want you to try the 3. And then I'm just going to avoid the fractions. Row 4, try the 6. Okay, and I'm going to pause the recording while y'all try this and see if any of you come up with one of them that will give me a remainder of 0. Okay, so after everyone tried this, y'all decided that the 2 is the only one that works, right? This is the one that works? Okay, so I'm going to show it up here now. So if 2 works, I don't know why I've got this hand. If 2 works, then I'm going to come in here. I do not know why I have this hand on here. Stop that. Okay, so if 2 works, I put the 2, the 3, the negative 11, and the negative 6. Bring the 2 down. 2 times 2 is 4. Add. 2 times 7 is 14. Add. 2 times 3 is 6. And yes, this makes us very happy. My remainder is 0, but I do not like this hand on my screen. I can't get it to go away. And I also can't get my recorder to open up. Where is it? Okay, did I lose it yet? Anybody see anything strange about this recording? Okay, now I'm back in action. Okay, so now what this means is we had, remember up here, this was originally a 3rd degree polynomial. So when I divide it by x, it's going to come down to a 2nd degree. So what I have now is this becomes 2x squared plus 7x plus 3. Okay, there's too much talking in the room. So then the 2 is a 0, which I factor as an x minus 2. So at this point, I have factored my function into x minus 2 times 2x squared plus 7x plus 3. Okay, so now it says list the possible rational zeros that we did, and then it says then determine the actual zeros. Well, to get the actual zeros, we have to fully factor this polynomial. So in other words, when I get an x squared term, I should be able to just factor it. Okay, I'm thinking that this is going to factor into something. All right, so I'm going to go off over here on a little piece of scratch paper and try to factor it. Now, this is my factoring method, which is a little unusual, but what I do is I take x plus something over 2, x plus something over 2. I multiply that 2 times that 3 and get a 6, and it's got to add to be 7, so it's a 1 and a 6. So I put a 1 and a 6. So this becomes 2x plus 1 times x plus 3. So here it is, factored. Okay, so now f of x is fully factored. It is fully factored. So now to find the zeros, I set each of these factors equal to 0. Right? I set each one equal to 0, and so I get a 2, a negative 1/2, and a negative 3. So this becomes the x-intercept, or the 0 of the function, at 2, 0, at negative 1/2, 0, and at negative 3, 0. These are the actual zeros of my polynomial. Okay, these are the true x-intercepts. Where did it go? This is acting really weird. And probably my hand's touching it strangely with my palm of my hand. Okay, so these are the... Okay, it's erasing whenever I do that. Okay, one more time. Let's see if I can make this work. Maybe I should not circle them. I'll just put an arrow at it. Okay, these are my actual zeros. And when I say zeros, these are my actual x-intercepts. Okay, so up here, the p's over the q's are the numbers in which somewhere in that list are my zeros, or a couple of my zeros, or something. But these are the actual zeros. These are the real x-intercepts of this polynomial. So you've got possible x-intercepts and actual x-intercepts of this function. And that's kind of the routine of how we do it. Okay, that's the routine of how we do it. Now let's go down further. Just one more thing. Let's see if I square this sucker, if it's going to erase or what. It stayed. Very good. Okay, so what I want you to do now is I also want you to just write this down. This is the factored form of your function. Okay, that is the factored form of your function. So you have your possible rational zeros, you have the factored form of your function, which gave you your actual zeros of the function. I'm going to try one more time to square this thing off. Thank you. Okay, so now let's head down. So all of those words you need to write down so when you look back at this, you know what in the world you're doing. So here we go again. List all possible rational zeros, then determine the actual zeros. How? By factoring through synthetic division. Okay, so here we go again. The number on the end is p. The leading coefficient now is just a 1. So my p is negative 5, and my q is a positive 1. So I list all the factors of these numbers, and there's not very many. 5 has factors of just 1 and 5, but remember you have the plus-minus version of each one. And 1 just has itself. So when I come in here to get the actual possible, and sometimes again they call them potential rational zeros, those are the p's over the q's. So my first p is a plus minus 1, so it's over 1. And my second p is plus minus 5 over 1, so I don't have a whole lot to choose from. Okay, I've only have 4 numbers here to pick from. Now normally I would distribute across the room and say each row pick one. Let's see which one of these is going to work so that I can put it into synthetic division. But I'm going to go ahead and just tell you, let's try the positive 5 for sake of time. Okay, for sake of time, let's try the positive 5 from that list. Okay, so here we go. 5 divides into 1x cubed, negative 2x squared, negative 14x, and negative 5. And remember, your goal is, goodness, I want the remainder to be 0 because that permits me to factor. So I drop the 1, multiply, add. 5 multiplied times 1 is 5, add the numbers in the column. 5 times 3 is 15, add the numbers in the column. 5 times 1 is 5. It worked. Okay, it worked. You may have had to try 3 or 4 times to get the number that worked, but that is the one that's going to work. So now what I can do is I can factor. It was an x cubed function, so now this is an x squared plus 3x plus 1. And I was using 5 as my 0, so this is x minus 5. This is my function almost completely factored. It is factored but not fully factored. Anytime you have an x squared term, you need to keep on factoring. You need to keep factoring it. And x squared you can just factor using your factoring skills. So this should factor into something like this. Now, is this going to factor? Okay, it'd be something over 1, something over 1. What will multiply to be 1 and add to be 3? That doesn't work, does it? Does not work. So in other words, this does not factor. Does not factor. Okay, so I'm supposed to be doing what? I'm supposed to be getting actual zeros. And actual zeros are where I set each of these factors equal to 0. Well, I've got the negative, I've got the 5 here, which we already knew through synthetic division that one worked. But what in the world do I do with the x squared plus 3x plus 1? Just give up. Honesty. Thank you. Okay. Okay. No, you don't give up. Look at this thing, okay? What is this? Oh, it is too fun. What is that thing called? The quadratic formula. And guess what? It works on a quadratic equation. It's not bad. Okay, so my A is 1, my B is 3, and my C is 1. Those are the coefficients of the x squared, the x, and the no x. So this becomes, let me move it up a little bit. This becomes x equaling negative b plus minus the square root of b squared. Well, I just got to do the b squared in my head. 3 squared is 9. Minus 4 times a times c all over 2 times a. Now again, when I do the b squared, I always just do that part in my head because you usually can. And it seems like it saves a step and it makes it look a little easier also. So this is a negative 3 plus minus the square root of 9 minus 4, which is 5. Well, that's kind of ugly, but that is the solutions. And there's 2 of them. One is the plus sign and one is the minus sign. So over here, this term is going to give me 2 solutions, and these are x-intercepts. They're going to be like decimal values. One of them is negative 3 plus the square root of 5 over 2 comma 0. And the other is negative 3 minus the square root of 5 over 2, 0. And those are my actual zeros of this polynomial. Darn it! I don't know why it's doing that. That was not easy to write. Good grief! Okay, negative 3 plus the square root of 5 over 2. And negative 3 minus the square root of 5 over 2. I will not square it off. These are your actual zeros. Okay, so you have the potential ones, and one of the potential ones worked. Only one of them. And now you have the actual ones. Okay, the actual ones. Okay. Okay, so yeah, you need to know that lovely quadratic formula, and I'm not going to square it off. Maybe if I put like a cloud around it or something. Okay, so now we're really happy because the difference in number 3 is they're going to give me a 0. Yes! Because if they give me 1, I have a number now to put through synthetic division. So if they give me a 0, I do not have to find the plus minus p over q, right? If they give me a 0, I don't have to do the p's over the q's. I've got a start number. I can just jump in this and start working it. So here they say, given that this is a 0, now go in there, find the remainder zeros by factoring. Okay. Oh, and look what I did. I wrote all this for you guys. Given a 0, we should not have to use the rational zeros theorem, okay? Which is the p's over the q's. So here we go. So put the 5 in. We have a 6x cubed, a negative 37x squared, 32 and 15. Bring down the 6. Okay, multiply. 5 times 6 is 30. Now add, multiply. 5 times negative 7 is negative 35. Now add. 5 times negative 3 is a negative 15. Add. This was supposed to happen because they told me that that number would work when they said that number was a 0 of the function. All right, so that's good. So now I'm supposed to factor this thing. So this factors now into an x minus 5 from the 0. And what is the other polynomial that's going to sit here? 6x squared minus 7x minus 3. Okay, now you're supposed to be factoring the 6x squared minus 7x minus 3. So to factor that, I'm going to come over here and kind of cheat a minute. Okay, so this is x plus something over 6, x plus something over 6. What multiplies to be a negative 18 and adds to be a negative 7. It's going to be a negative 9 and a positive 2. So this becomes x minus 3 halves and x plus 1/3. So I push the 2 up into the front and the 3 up to the front, and I have that trinomial factored. So this becomes x minus 5 times 2x minus 3 times 3x plus 1. And remember, I do have a recording posted where you can watch that factoring process, and it's quick. Okay, it's not going to take long to learn it. I just threw my mouse on the floor. Okay, so I'm supposed to factor it. So this is the answer for factoring, which I'm terrified to box off, but you should put that in a box. Okay, that is your factored function. And then to find the zeros, you set each one of these factors equal to 0. So you're going to get x equaling 5. So there's an x-intercept 0. You're going to get x equaling 3 halves. There's another x-intercept 0. And then you're going to get x equaling a negative 1/3 for my third actual zeros. So these are the actual zeros, the actual x-intercepts of this given function. So you have it factored and you have all x-intercepts. And you did that because they were kind enough to give you a number that when placed through synthetic division gave you a remainder of 0. Okay, so I've got that part highlighted. Okay, so the next one's going to take a fraction through the process. Oh, no, it's not. Okay, I thought I had it printed here. This is not going to be a fraction. Okay, so this one, I'm going to pause the recording, and I want you to try it. Okay, you can talk to each other, but I'm going to pause the recording because I want you to try it. Okay, so when you put negative 3 through synthetic division, this is 6x cubed, 19x squared, 2x, and a negative 3. And you bring down the 6. Multiply, add, multiply, add, multiply. That sucker better give me a remainder of 0 because they said it was a 0. Okay, so remember in the parentheses, this is x minus the negative 3. You subtract that 0, and this is 6x squared plus x minus 1. Okay, here comes the factoring for those of you who are not sure what I'm doing. Okay, so I put x plus something over 6, x plus something over 6. I take the 6 times the negative 1 and say what multiplies to be that negative 6 and also adds to be that coefficient in the middle, which would be a negative 3 times a positive 2. So this reduces into x minus a half and x plus a third. Then I push the 2 up to the front and the 3 up to the front of the x. So this factors now into x plus 3, 2x, yes, I'm sorry, that is a positive 3 and a negative 2. A positive 3 and a positive 3 and a negative 2. Okay, so thank you for catching me on that. Here I am trying to hurry. There we go. So this becomes 2x plus 1 and 3x minus 1. Okay, so there is the factored version, and they're going to ask you, they say factor this. This is your answer for the factored version of the polynomial. Okay, then they ask you, given this 0, find the remaining zeros. So to find the remaining zeros, you set each factor equal to 0. So I get x equaling negative 3, x equaling a negative a half, and x equaling a positive 1/3. So I have a 0 at negative 3, 0, negative 1/2, 0, and 1/3, 0. So these are the zeros of the function, which we also know are referred to as our x-intercepts. So we factored it. And we also found all of the x-intercepts, all of the zeros of the polynomial. Okay, all of the zeros of the polynomial. Okay, so they are going to ask me now to use a fraction this next example, but it's not difficult. They give me a pretty easy number to work with, so it's not bad, so you don't need to avoid it. It works out pretty nicely. Okay, so here we go. I'm so afraid to square these crazy things off. It's hard to not put those things in boxes. Okay, here it is. Your 0 is a negative a half. All right, so if I put a negative a half in, then negative a half, and remember, if they give you the number, put the number in the half box. If they give you a binomial, you change the sign to the half box. Okay, so 2x to the 4th, negative 1x cubed, 17x squared, negative 9x, and negative 9. Multiply. Negative a half times 2 is a half of 2, which is just 1, but it's negative 1. Add. A half of negative 2 is 1, and a negative divided by a negative is a positive. Add. A half of 18 is 9, but it's going to be negative. Add. A half of 18 is going to be 9, and a negative multiplied by a negative times a negative is a positive. So you can see they purposely made this so that it is not that difficult. Okay, they really have purposely made this so it would work for you nicely, and it better have a remainder of 0 because they gave it as a 0 of this polynomial. Okay, so now I can factor, and remember it's going to be opposite of the sign, so it's x minus the negative a half. This was a 4th degree? Yeah, it was a 4th degree polynomial up here. It's a big one. So this becomes an x cubed. So this is 2x cubed minus 2x squared plus 18x minus 18. And now I remember why I chose this one. Okay. In this textbook, they're really pushing this factoring. And when you get a cubic or a 3rd degree polynomial instead of a quadratic that we know how to factor, this is grouping. So let me show you this real quick. This is a reason why I selected this question. It's like, haven't we done enough examples so far? Well, I want you to see this. If you have 2x cubed minus 2x squared plus 18x minus 18, if you've taken any developmental classes on campus, this is very familiar to you. This is called factoring by grouping. which means you put parentheses around the first two terms and parentheses around the last two terms, but leave that plus sign down the middle. You look at the first binomial, you take out the greatest common factor, which is 2x squared, which leaves behind an x minus 1. Then you take an 18 out of the next one, leaving behind an x minus 1. Now, if they give you a cubic like this to factor, you should be able to group like this. They're going to rig it up, or they're going to set it up so you can factor. So now if you remember, this is an x minus 1 times. Now if I cover up the x minus 1s, if I cover them up, it's going to be what goes in here. Anybody remember? 2x squared plus 18. Now there is one more step to this, because you can take a 2 out of this, leaving behind an x squared plus 9, right? Okay, so back over here. This is x plus a half times x minus 1 times x squared plus 9, and then the 2, we'll put it up in the front. There is your polynomial. Now here's an x squared term, and we're supposed to factor those, but that's not going to factor. If it was x squared minus 9, I could factor it, but plus 9 cannot factor. So what do I do now to get the 0? So this is the first answer. This is your function in factored form. Okay, there's the first answer, but now to get the zeros, I said each one of these factors equal to 0. And remember, if you try to set the 2 equal to 0, that's false. If it were 2x, you could do that, and then x would be 0, but there's no variable with it, so you cannot get a 0 out of it. So this becomes x equaling a negative a half, x equaling 1. Oh, what's going on here? This is interesting. Oh boy, what is this? We used to not be able to do this, but they're going to tell you to do it now. Somebody tell me, what does this mean? Now we can do this, because they're going to let us go into the world of imaginary numbers now. So what is this? Plus minus 3i. Remember that? Okay. Because remember, the square root of negative 9 can be rewritten as 9, square root of 9 times the square root of negative 1. Square root of 9 is 3, and the square root of negative 1 is I. So remember, I squared equals negative 1, which means I is the square root of negative 1. Okay, so this is all when they throw you into the world of imaginary numbers, okay, that's where it's coming from. So when they ask for the zeros, you're going to have negative 1/2 0, 1 0, and then you're going to have 3i 0 and negative 3i 0. You have 4 zeros to this polynomial. It was a 4th degree polynomial, and so you will have 4 zeros. Now, at this point, 2 of them are true x-intercepts. But these 2 are on the imaginary number line. And we're not going to have a third dimension with an imaginary number line. So they just call those the zeros. So when it's not really an x-intercept because it's an imaginary number, then that's why they are using the word zeros rather than x-intercepts. Okay, just get that vision. So let me repeat. Let me scroll up for just a minute. Good grief, it's way up there. Okay, this was a 4th degree polynomial. And if I'm going to include imaginary numbers, I will have 4 zeros. Now that's some pretty cool stuff. Pretty neat stuff. Okay, so now we're going to move down into the next section, which talks about the fundamental theorem of algebra. And here's where we really get into the number of zeros and talking about the zeros being complex. When we start talking about complex, we have real numbers, and now we have imaginary numbers. When we take all the real numbers and add them to the imaginary numbers, collectively, this creates what we call the complex number system. Okay, so when we start playing around with i's and real numbers, we get into the complex number system. So when you see something like 2 plus 3i, you're combining a real number with an imaginary number, thus creating a complex number. Okay, so that's where we are now. So it says if we're working with complex numbers and complex zeros, then the degree of the polynomial will tell me how many zeros I have. So if I have a degree of 3, I will have 3 complex zeros. Now we do have to include multiplicity when we do this, but we're going to come up with 3 complex zeros. What is the degree of this f of x in number 2 here? What is its degree? 6th degree polynomial, which means we should get 6 complex zeros from it. Now, we will have to include multiplicity, but we should come up with a total of 6. And that's what it says up here in these words. Provided that each zero is counted by its multiplicity, we will get all 6 complex zeros. So if you've never seen imaginary numbers, it doesn't get really deep. It's pretty basic, and so you'll be okay. No reason to panic. We have this conjugate zeros theorem, and what it says is that if a plus bi is going to be a 0, then a minus bi must also be a 0. So anytime you have a complex number as a 0 of your polynomial, they come in pairs. They always have to come in pairs. So in other words, part 1, examples of conjugates, if 4 minus 5i is given to you to be a 0, 4 plus 5i will also have to be a 0 of that polynomial. One will be addition and one will be subtraction. You must always have your complex zeros in pairs, an even number of complex zeros. Okay, so let's look at where this goes. Look at number 2. Given that 3 minus I is a 0 of this polynomial, find the remaining zeros and factor. Okay, so immediately, if 3 minus I is a 0, 3 plus I is also a 0, because you must have, they must come in pairs in what we call conjugate pairs. Now, in the textbook, they teach you to take this complex number through synthetic division, and it's very long and it's very tedious. So what I suggest you do is maybe skip the knowledge of putting a complex 0 through synthetic division and just go straight to your plus minus p's over q's. Alright? Because trying to put 3 minus I through synthetic division is not easy at all. So how do we do this? I'm going to let you cheat just a little bit. And the way you do it, I'm going to even let you cheat this, is if you go to the calculator and you graph on your calculator y equaling x cubed minus 2x squared minus 14x plus 40, and you look at the graph, you will be able to see that it has an x-intercept of the point, let me look real quick, -4, 0. Okay, so if you graph it on your calculator, you will be able to see that -4 is an x-intercept. So I'm going to let you do that. Now on a test, I will ask you to be sure that you list all rational zeros so I know that you know how to find them. But beyond that, I will let you use a calculator rather than just checking over and over again through synthetic division. Okay, so now having told you that on a graph, this line has this x-intercept, we're going to jump in and see what happens through synthetic division. Okay, through synthetic division, I have a 1x cubed, a -2x squared, a -14, and a 40. So, bring down the 1, multiply, add, multiply, add. Negative 4 times 1 is negative 4, add. Negative 4 times negative 6 is a positive 24, add. Negative 4 times 10 is a negative 40, add, and yes, that better give me a remainder of 0, because this means that negative 4, 0 is an x-intercept when the remainder is 0. So I have an x-intercept, and now I can factor my polynomial. At least my first step of factoring will be x minus the negative 4, and it began as an x cubed polynomial, so it's going to come down to an x squared. So this is 1x squared minus 6x plus 10. So that's my first factorization. Now, is this x squared minus 6x plus 10 going to factor? No. This sucker is prime. So I can't do this. All right, whatever. So what I do have is I have it factored to the x plus 4 times x squared minus 6x plus 10. So to find the actual zeros, this is as good as it's going to get in the factored form. It's factored. It's not going to factor any further. But to get my zeros, as before, I set each one of these factors equal to 0. Now the first one comes out quite nicely, and we already even know this one. But what do I have to do to get the zeros from the x squared minus 6x plus 10? Go to the quadratic formula. Okay, so my a equals 1, my b is negative 6, and my c is 10. So how to remember the quadratic formula? X equals negative b plus minus the square root of b squared minus 4ac all over 2a. So if you watch the recording, you will learn that melody, okay? Okay, so this becomes x equaling a negative of a negative 6. Now be sure the negative is from the formula, and the b is another negative 6. Plus minus the square root of 6 squared, which is 36, minus 4 times a times c, all over 2 times a. That melody is Pop Goes the Weasel. Okay, so this becomes x equaling 6 plus minus the square root of 36 minus 40, which is a negative number. Okay, I'm going to have some imaginary solutions, right, or some imaginary zeros. This is now 6 plus minus 2i over 2. And you can simplify this, but you have to, every one of those numbers better simplify together. So the 2 goes into the 2 once, the 2 into the 6 3 times, and then the 2 once. And this becomes 3 plus minus 1i. So you've been working hard over there on that right side of the page. Come back to where your answer area is. So from this second factor, my zeros are 3 plus I, comma 0, and 3 minus I, comma 0. And those are the zeros of this polynomial. It was given to me to be a third degree polynomial. There are 3 zeros listed. 2 are imaginary or complex, and 1 is real. Pretty nifty stuff. Okay, so we've done a lot of examples, so I'm hoping that you feel pretty comfortable with that, relatively solid. I think it gets a little bit easier now. So now what we're doing, be careful that you read the title. We're finding the equation. Okay, find the equation. We got to figure out what in the world is f of x. And this is not bad. Okay, this is not bad. So take a look at this question. I think we've done a little bit of this already. Find the polynomial of degree 3 with zeros at -3, -2, and 5. All right, well, f of x will equal x minus the 0, x minus the 0, x minus the 0. So this becomes x plus 3, x plus 2, and x minus 5. That looks pretty darn good. Now, we're missing something pretty important, and that is a leading coefficient, because if it's positive or negative, that tells us in behavior. We're missing that number, and it also tells us vertical stretch. We're missing all of that. So you'll often see them put A there, like A is a number, and we need to figure out what A is, okay? So they'll sometimes put an A there, and we need to figure out what that A is. This is why they've given you this information that f of -1 equals 6. Well, that's function notation for the point -1, 6, which is going to be on this line. Well, if that point is on the line, and I take this out of function notation and just make it a y equals equation, okay, take it out of function notation and just make it a y equals equation, then take this ordered pair and substitute it in for the x and y variables, you will find the value of A. Okay, so let's see if that really works. Y is 6 and x is -1. Now this is not hard, so don't mess up here. So this is 6 equaling A times -1 plus 3 is 2, -1 plus 2 is 1, and -1 minus 5 is -6. So this is 6 equaling -12A. And when you divide both sides by -12, you get a -1/2. So now we really know the function. Okay, we almost had the answer up here, and I'm terrified to square it off. Okay, for fear it'll erase it. Okay, this is almost the function. But now the real answer is, put that A in there, your answer is that f of x equals the -1/2 times x plus 3 times x plus 2 times x minus 5. That is your function. Is that a third degree polynomial? Yes. And we know the vertical, it's not a vertical stretch, it's a vertical shrink, and we know that somebody also reflected it over the x-axis. Isn't that neat? That's not hard. Okay, that is not a difficult process, and we did come up with the name of the function. If you graphed it, you would see those x-intercepts, and you would see it passing through the point -1, 6. Okay, pretty cool stuff. So here's another one, pretty much identical to it, right? So it's another third degree polynomial. Here's your zeros. Remember, you subtract these. So it's x minus a -1, x minus 2, and x minus 4. But don't forget, we don't know the leading coefficient. We don't know the vertical stretch or shrink. We don't know if it's reflected over an x-axis. So we're going to leave that as an A for a little bit until we can come up with the value for A. So this is almost the answer. We need to find A. And the only way to find that A is if they give me a point, an ordered pair point, to use into this function. So they give it to you, and they're always going to give this to you in function notation. This is the point 1, 3. So the 3 replaces the y, or the f of x, and the x will be 1s. So 3 equals a times 2 times negative 1 times negative 3. That's a positive 6a on the right side. And so oddly enough, and this is not normal, but your a value turns out to be a half again, but this time it's a positive a half. And so your answer is that your function is a positive 1/2 times x plus 1 times x minus 2 times x minus 4. Now when you get into your homework, this answer is in factored form. I'm not sure. They might require you to multiply it out, but if they say show your answer in factored form, which is how I will put it on a test, then that's as far as you need to go. You don't have to multiply all that out doing FOIL and a whole bunch of distribution. You can leave it in factored form. I believe we have one more. This one. The only difference in this one from the prior two is all of a sudden they give me multiplicity. Okay, they give me some multiplicity. So they only give me 1 0, which is occurring at the number 4. So all I have is x minus 4. But I can put that x minus 4 to a power, right? Because the multiplicity is 3. That means I'm supposed to put a 3 on that binomial. Okay, so that's the difference from this question as compared to the prior two. So again, this is almost the answer, but I still have to find A. And to find A, I have to use this last piece of information they give me in the question. So I replace the y value, which is f of x. I replace the f of x with the negative 24 and the x with the 2. So this becomes negative 24 equaling a times a negative 2 cubed. This is negative 24 equaling, okay, negative 2 cubed is negative 8. And finally we get an a value that's not a half. So my function, and this is considered the factored form of it, equals 3 times x minus 4 cubed. There is your answer. There is your function. But this answer is in factored form. Now on the test I will write, give your answer in factored form. Okay, but in Connect Math you might have to multiply that out, which is kind of time consuming. So be very careful with it. Okay, you guys were wonderful. This is a pretty long recording, but I'll get it produced and get it posted for you.